Thanks, Gemma. Thanks for inviting me. I'm going to be talking about ParaDiag methods and about work that has been going on at Imperial for the last few years. I've been there for 3 years, but it kind of started with Colin and Werner and Lawrence before me. Abdulaziz was another postdoc who's now at Bath, who was involved with the project. And a lot of it has been funded by the Met Office and UKRI through the Excalibur program. It's Colin. So I'll go through the ParaDiag method. You've seen a topic given before. The slides will look very familiar. More and more people are familiar with ParaDiag now, so that's good. I'll talk a bit about briefly about Askew, which is the software library we've been writing. I'll go through some atmospheric models, and then how much time I have at the end for some new results on conversion testing. So, we go through, we're looking at time-dependent PDEs. We use finite elements, so we always have this mass matrix on the time derivative. I'm just going to be looking at, for the most part, at implicit theta method. That is what we have in Askew, but ParaDiag isn't limited to that. So you end up with implicit theta, Euler, explicit Euler, trapezium rule. So put it into an all-at-once system that most of us, I think, are very familiar with. We have one row per time step. You have this recurrence relationship. The theta method, this is what it looks like if you break it out in Kronecker product form. So you have this B1 and B2 matrices that describe the time stepper. So for different time stepping schemes, this mass and stiffness matrix will be the same, but B1 and B2 will change. And ParaDiag 2, which is the that we've been working on, preconditions this equation, this matrix with a alpha circulant approximation. So circulant matrices, which are periodic, are simultaneously diagonalizable by the FFT. Alpha circulant matrices, where this alpha is a small coefficient, but also simultaneously diagonalizable with a weighted FFT. And the important thing about them being simultaneously diagonalizable, if these V's are the eigenvector matrices and the eigenvalue matrices, you have this factorization. So to apply this preconditioner, you do an FFT in time, you do a block solve in space for each frequency, like a backwards step with the complex delta V. And you can do those in parallel. Every frequency is decoupled. And then you do an inverse FFT to get back again. Block solves that you do in the middle, one of the really important things that we found with ParaDiag is that the D1 and D2, the eigenvalues of these alpha circulant matrices, you end up solving blocks of this form. So if this is the one in the serial in time, the implicit solve in the serial in time method, this is what you solve in ParaDiag for each, and there's a pair of eigenvalues for each frequency. And if you plot these, the ratio on the complex plane, if you have this many time steps in your all-at-once system, to begin with, you're essentially at unity. So these look very much like the original ones. And you can basically use your normal serial in time solver. The more time steps that are in your all-at-once system, the more spread out these time steps become. So you end up here with time steps that look like they are very large and very imaginary, which is not a nice place to be. Similar to the systems that you see in Rexy, if you're a wave equation, then these look like very, very indefinite Helmholtz, which have eliminated down to a single variable. So the big thing with ParaDiag is not just the parallel in time level, but actually how do you solve these systems where you can't just, like with ParaReal or MGRIT, you copy over a solver for serial in time. So for constant coefficient problems, there's many results on very good convergence. This one in particular proves it for any stable time stepping scheme. You have a convergence rate of alpha over 1 minus alpha. So if alpha is 10 to the minus 6, 10 to the minus 8, you're converging very, very quickly. You're only really limited by the machine precision. So that's really, really nice, but it's only for constant coefficient linear problems. For non-linear problems, you have the function evaluation at each time step. So the function is dependent on the solution, which means that your Jacobian, each column of the Jacobian is no longer just a shift of the previous column. That you can't immediately make a circulant matrix that needs this vertical shift each time. So instead, you replace the spatial Jacobians with some approximation. So what matters is that the approximation is constant at every time step. You can do that as an average of all of the Jacobians. You can do that as an average as the Jacobian of the average solution. You can pick a completely different solution to take a Jacobian around, as long as it's constant in time. And then you can get back this Kronecker product structure. The only problem is now you have this additional error in the preconditioner. Non-linear problems, we have the original problem. We have a all-at-once system with this vertical concatenation of all of the function evaluations. We have the Jacobian that is different at every time step. And then we have some preconditioner with a circulant approximation and an average approximation. And as far as I know, the only previous result for convergence in the non-linear case, or the variable coefficient case, is from Gaia Chaklovich in her thesis, where you have these terms, which are the original convergence rate. And then you have this section, which is the total duration of the window. So it's of the all-at-once system. So the longer your window, the worse your convergence rate. This L is a Lipschitz constant of the difference between these two. So it just measures how bad is your averaging approximation.
And what was C?
Oh, C just depends on the method. So Guy was doing allocation methods. So that has a factor of the Q and a couple of other things. It just depends on that, yeah. Brief performance model, just so when we're looking at results later, we kind of have an idea of what we're looking out for in terms of how do we get a good method. So in the serial method and the parallel method, time serial and time parallel, the majority of the work is solving linear systems that resemble that top row, where we have just different coefficients in each case. So if we say the work involved is proportional to K, serial in the parallel method, which is the number of Kovalov iterations to solve this, assume we're using an iterative method, it's proportional to MS in the serial case, so the number of Newton iterations per time step, which is the number of times I have to solve one of those systems for each time step I want. And in the parallel case, this MP, which is the number of applications of the preconditioner per window solve. So the total number of Kovalov iterations across the entire window solve, because again, that's the number of times I have to solve a system that looks like this. And then we have a dependence on just the total number of DOFs. So the spatial DOFs and the degrees of freedom and the temporal degrees of freedom. And then we can parallelize in space only in the time serial, parallelize in space and time in the parallel method, and we double it because we're in complex arithmetic, so you can actually squeeze out an extra, or almost an extra 2 times speed up. So then in the serial case, the reason why we're all here is because this has a linear dependence on the number of time steps, whereas we hope that this doesn't. The extra bit for ParaDiag is this TC. So because we do an FFT in time, and then we do a block solve in space, we end up having to do some kind of transpose. Whether you do that implicitly with the parallel FFT, if you do it explicitly, you do MPI all to all, and then the FFT, it can get very expensive. So our performance model is that we are linearly proportional to the number of time steps. We are inversely proportional to these two metrics, which are how many more iterations does it take to solve each block than in my serial method? And how many more times do I need to solve the blocks? How many more ParaDiag iterations do I need versus this Newton iterations per time step? So I really want to control these two. This one, the communication time versus the block solve time, can reduce this and I can have a sensible all-to-all strategy, but kind of up to the MPI vendors to a certain extent. We'll see how much of an effect. So SKU is a library that we've been writing because ParaDiag has a lot of different levels. You have the all at once non-linear solver, all at once linear solver, then the block problems. So SKU is a sandbox to try out a lot of different methods using firebreak and PETC. Some of you were at the session earlier. I'm happy to talk about SKU to as many people as are interested. We can do any PDE that we've tried so far of unified form language, expresses finite element methods. We have linear and non-linear methods. We're space-time parallel. Yeah, we want to be a flexible sandbox, but still have good scaling on HPC machines. The space-time parallelism is provided by Firedrake's ensemble, where we just have a Cartesian product of communicators. So we have each time step lives on a blue spatial communicator. You can have multiple time steps per communicator. And then the gray communicators communicate in time, so they connect the same part of the mesh at different time steps. So block solve on the blue, f of t on the gray. And that just helps us manage the communications. I'm not going to go into SKU in depth, but this is a complete script for running the heat equation, parallel in time, and possibly parallel in space with ParaDiag. Fit it in 43 lines, which is quite nice. Obviously, they get more complex, but the results I'm going to show you later, the scripts look very much like this. The difference is we have different finite element forms here, we have different solver options here, but that's what that ParaDiag script looks like. Okay. So we've got a method where we can use the FFT to decouple a whole load of different frequency modes. Once we have decoupled modes, we can solve each one in parallel, where we get a complex valued backwards Euler step. For the non-linear methods, in addition to the periodic approximation, we have an averaging approximation. And we have a library to explore all of this. So I'm going to go through some examples. I've shown some of these examples at previous meetings and conferences. Up-to-date results and a new case. Some of them are a little bit better than before. Some of them are much better than before. Quite exciting. So to begin with, I've just got scalar reduction equations. So we start simple. The kind of canonical hyperbolic problem. It's very simple, but a lot of parallel and time methods struggle with it. So we're just going to do a simple fixed point iterations, block solve on, LU on the block solves, and run a variety of alpha values. So this is showing the wall clock time it takes per time step for different values of alpha when we increase the number of time steps in the window. So this is 2 time steps in the window, 16 time steps in the window, 250 time steps in the window, and you just divide the solve time by the number of time steps. What you can see is you get very, very good convergence all the way out to several thousand time steps. This has, I think, a tolerance of 10 to the minus 10, so 10 orders of magnitude. And this one takes 10 iterations, this one takes 5 iterations, this one takes just over 3 iterations. You see the perfect scaling. And then we have some of the speed up. So getting up to a speed up of 520 at the top end, because we're constant coefficient, which is exactly the scenario is built. Quick bit of a profile. This is now rather than per time step per solve, just to show that we have an efficient implementation. Is as you increase the number of time steps, the total time to solve the whole window per time step of the whole window, you want to stay constant, because then you can keep on adding more windows, more time steps, and you only have to wait the same amount of time. You can see that almost everything scales very, very well. The block solves, the action of the Jacobian evaluation of the function of the residual, and the FFT is essentially negligible. The thing that really cuts into our scaling is this transpose, which is the global communications. So that's the reason why we start to lose scaling. But we lose scaling at like 4,000, 8,000 time steps. So we're fairly happy. We're still fairly happy with reaching that point for perfection. So The next one we moved on to is still linear, no constant coefficient, but this is the linear shallow water equations. So it's a wave equation. So now we're mixed function space with velocity and depth. And this is using finite elements, which is Gemma and Colin in a lot of detail about. It's going to be used in the next Met Office model. It has a lot of nice properties, a lot of conservation properties. Doesn't show any of the grid modes that you often get with these types of mixed problems. This time we're going to use FGEMRES, not because we need the flexibility, but it saves us one iteration, which if you're only doing 3 Krylov iterations, not having the extra preconditioner application does make a difference. And with the block solves, we use a hybridization, which is where you essentially eliminate down to a single variable on the element facets. So you get a much smaller system to solve. Test case is on the sphere. So you end up with a few Gaussian bumps in the depth field, and then it essentially looks like you just dropped some stones in a puddle. Propagate around. So for this case, this is now space parallel as well as time parallel. So we have 4 cores in space for the time parallel method, 2 cores in space for the time serial method. We run 2 different values of alpha, and then this line at the bottom is the predictions of the performance model. So taking the serial in time method, which is the dashed horizontal line at the top. So this is how long it takes per time step. If you just do serial in time, obviously no matter how many time steps you do, that's constant. So you can see that as we increase the number of time steps in the window again, we get very, very good scaling, just like the advection problem, and it's constant coefficient, a fixed number of iterations. So we end up with a speed up of about 2000 once we get to 8000 time steps. We're pretty happy with it when it came back. I reran a couple of cases because I didn't quite think it had run properly. I wasn't convinced it was. They agreed. One of the things that's gone into this is, again, doubling the number of cores we use for space parallelism because we're complex arithmetic. So double the number of operations for addition and subtraction, but more than double if you do multiplication. So depending on what you're doing, it can actually increase your arithmetic intensity doing exactly the same thing in complex arithmetic versus real, which is quite nice for something like finite element methods, which are very bound. First non-linear case, we have the non-linear shallow water equations. So now we have an advection term. And again, compatible finite elements, the trapezium rule, and we're doing a Newton FGEMRES and moving to an iterative solver on the blocks. So a GMRES and a patch and additive Schwartz method multi-grid. Gilensky test case where you end up with this jet becoming unstable and developing on it for 10 days. So we have several different mesh sizes from 50,000 degrees of freedom in space up to almost 3.5 million. We're running out to 10 days, which is more time steps than we can do in one all-at-once system efficiently. So we've run out with all-at-once systems of 2 time steps at a time, repetitively, or 4 time steps, half as many windows in total, so on and so on. So these open symbols are the serial in time results. So every time we double the mesh resolution, we also increase the temporal resolution. So our delta t decreases, go out to 10 time steps, total number of time steps increases, and you get this linear increase in the time it takes serial in time, even though we have very, very good weak scaling. But once you move to using ParaDiag with this Newton-Krylov method, you can see that when we move to 2 time steps in the window, 4, 8, 16, 32, we do start to see some decent speed up, especially at the higher resolutions. So we have the maximum speed up here for each resolution. And we get some nice weak scaling results at our time, but happy if anyone wants to ask questions about that one. But once we've reached this maximum speed up, we see very quickly that the speed up just tanks as soon as we increase the time step. So if we look at Y, we look back at what our speed up looks like. So we have way fewer numbers of time steps than where we had issues with communication. So we just knocked out that term. We see for the block iterations, for the solving for each mode, as we increase the number of time steps, it increases the number of iterations it takes quite not very, very quickly, but as soon as you get to a certain point, it does start to increase and it collapses on the number of time steps, because no matter what your resolution, it's the number of time steps in the window that determines where your time step is on that complex plane. So block iterations collapse on the number of time steps in the window. The all-at-once iteration, so how many ParaDiag iterations it takes to solve each window, scales on the duration of the time of the window. Because no matter how you chop it up, as long as you're reasonably resolved, if you have a fixed window duration, you have a certain amount of variation around the average, no matter if you chop it up into 8, 16, 32 time steps. But to collapse the outer iterations, you have to plot against the window duration. And that, yeah, comes out in this part of the conversions. So one of the things we tried specifically to target this problem is pipeline Gauss-Seidel iterations. You can also think of it as parallelizing over the Newton iterations. So you do 1 Newton iteration on the first window. So this is your time series up at the top. And each of these is a full interval of like 8 or 16 time steps. So to begin with, you do a Newton iteration on this one, and then you use whatever value you have here with the initial guess for the next one. Iteration on both of them sequentially. Keep on doing that until you filled the pipeline. So then the idea is that after each iteration, you check if the one at the back of the pipeline has converged yet. And if it has, you drop that, move those processes up to the next one. So once you've filled the pipeline, every time you iterate, ideally, you end up at the point where you converge a new window at every iteration. Sometimes that doesn't happen. So here I've demonstrated they're not converged and you just need an extra iteration. But if we do that, then again, plotting the number of ParaDiag iterations against the duration of the window. Purple is all the results before for all mesh resolutions. But if we now plot sequential Krylov iterations per window, which is the total number of Krylov iterations you take divided by the pipeline depth. Because if you have a pipeline depth of 5, you're doing 5 iterations at any one time. And you can see in green, if you do 2 of them in parallel, it drops the number of iterations you need a bit by about a factor of 2. And then if you increase it to 3, a bit further, 4, a bit further still, and it's very scalable at the first step and then kind of less so. It does start to bring it down the constant point. This gets a bit unstable. It's still a non-linear problem and you're doing things very inexactly, but it does start to flatten this curve. And if you look at the equivalent speed ups that you get, the black this time are the serial, are the single window, so the original Newton-Krylov method for each mesh resolution. So you can see you start to get speed up, and then at a certain point, your scaling just tanks. But if you do the pipeline Gauss-Seidel with, say, window lengths of 4, simultaneously, window lengths of 8, multiple windows simultaneously, you can extend your scaling by an extra factor of 2 to 3, depending on what the resolution is. So here, we've essentially reduced the number of iterations needed per window by a factor of 3, and we get a 3 times speed up. So you can only parallelize by the number of iterations it takes per window, so it's limited, just like if you're pipelining instructions. But for that small scale parallelism, you do get some very good scaling. Okay, that's shallow water. So the shallow water's a useful test case because it gets the entire globe and you get external gravity waves. I got a nod from Gemma, I got it right. And you have the convection. What you don't have are the internal gravity waves. So the vertical slice equations gets you a 2D vertical slice of the atmosphere, and you solve compressible Euler on that slice. So we have velocity equation, density equation, potential temperature equation. Well, it's non-linear, and you have the embedded wave equation, like you would do with standard compressible Euler. You also have a linearized version where you linearize around a state of rest. So this is explicitly just isolating the wave, the wave phenomena. The test case for this is an internal gravity wave. So you have a constant background flow. And then on top of that, this is the temperature perturbation, where you have gravity waves kind of oscillating up and down and then propagating through. So it is nonlinear, but the background reference state is very benign. It's this constant background velocity. And this time we're going to look at block solves. So what can improving your block solves take? To begin with, we are going to look at column patches, which is just doing, again, an ASM, but then rather than a small patch around a particular vertex or element, we do column patches. So we take an entire stack of elements and invert that monolithically, which is a method that Colin and Gemma used recently for serial in time method and got results with CFL independence. Very nice, because you can resolve, keep on resolving in time and space, but iteration counts don't increase. We're also going to look at composing it with the linearized equations. You do an iteration of an ASM, additive Schwartz method, and then you do an iteration where you just use the linearized equations around the state of rest as a preconditioner. You alternate between. On the left, we have the speed up for various methods. And on the right, we have the block inner iterations. So we see the serial results. For the serial case, just the star patch, so the column patches, is faster for the serial in time method. The composite one, very good convergence, fewer iterations, but each one is more expensive because we're alternating between the methods, so it's actually slower. However, once we get to using it for ParaDiag, if we just use the column patches for the blocks in ParaDiag with the green one, we don't get particularly good speed up versus the two. Disappointing. It's essentially because the numerical domain of dependence for the column patches is linear in the number of iterations because it only couples neighboring cells. But as your coefficients for those frequency blocks increases, it looks like a larger CFL. So actually it looks like a larger time steps that's coupling more elements, and the method doesn't capture that. If you combine it with the composite preconditioner, where you alternate between a global linearized solve and then the column patches, you can get significantly better convergence out to a higher number of time steps because it's getting this local treatment of the advection, global treatment of the wave, local treatment of advection, global treatment of the wave. So sometimes the optimal serial in time solver is not the optimal parallel in time solver for the blocks. And then on the last one, we just tried changing up what the convergence criteria was for the blocks. So normally we'll do a fixed tolerance, so converge every block to a certain tolerance. And what we find is that some blocks get very, very hard, very, very close to the imaginary axis, and they take a lot of iterations. Some of them end up on the real axis, way far away from the imaginary axis, so they're essentially a mass solve. So those ones are really, really easy. So if instead we fix the number of iterations we allow on each block, we go, I'm going to undersolve the difficult ones, but I'm going to oversolve the easy ones and hope that that kind of balances out. You can squeeze a bit more out. We just picked increases with the square root. The square root of the number of time steps block iterations because it needs to be sublinear if you're going to get any speed up. Then this is what you should do entirely, but it's just showing that you can play around with your block solver to make quite a big difference in the speed up that you get. Reasons for this speed up tanking once we get to really high numbers of time steps, or reasonably high number of time steps for a non-linear problem in the window, is also because the number of outer iterations increases. Because each ParaDiag iteration you're only partly solving. We're not solving to a particular tolerance, we're just taking a certain number of iterations and then stopping. You pay for that by the fact that your outer iterations increases. So you're just moving work from one place to the other, and you hope in the kind of optimization you find a nice minimum. Okay. Very long time on a train yesterday, and my throat is quite dry. Okay, so on through the method. Touched on the software library askew, gone through some models for atmospheric flow of increasing complexity. So linear, single field, linear, multiple field, non-linear with strong advection, non-linear with some strong wave components. We've shown how the outer iterations and the inner iterations both can have quite a big effect on the speed up that you get, which agrees with the performance model that we've worked out. But we'd still like to know a bit more about quantifying why or how the convergence reduces so much when you're not in a constant coefficient problem. So when you also have this averaging. So for general propagators. So we'll now do what's probably more familiar expression for the all-at-once system for a lot of people. So we've done the one Jacobi preconditioner. So we now have identity on the diagonal. We have our propagators phi. Go from one time step to the next. And I'm going to write my kind of general all-at-once operator, the function of the propagators alpha. So if I have just phi rather than phi j, so a constant in time, and my alpha is 0, that was our original one. Phi and alpha was our normal preconditioner. That's this combination of preconditioner with constant coefficient alpha. But we're also interested in this one, where we have our all-at-once operator varies in time, so it's a function of the time step. And our preconditioner, this phi hat, the hat just means it's the propagator in the preconditioner and it doesn't match the one in the matrix. So anywhere you see a hat, that's all it means. It's just, it's a value in the preconditioner that is different from the value in the matrix we're solving. So what we'd like to do is estimate the convergence bound for the fixed point iterations. So standard expression for the convergence with this P inverse P minus A. And the way we're going to go about that is there is a time series that's implied by the circulant preconditioner. So if we have an expression for this time series, we can then plug it into the error equation. This right-hand side, A and P are sparse and very structured with the same structure. So this is pretty straightforward to calculate. And then we can work out an expression for the error at the next iteration based on our time series. What we're going to do is we'll go through that, and then we'll re-estimate standard ParaDiag convergence, show how it falls out in this approach, and then we'll use it to estimate the convergence for variable and inexact. So in Gander and Wing, 2020, they give the time series solution for the circulant all-at-once preconditioner for the homogeneous problem. So you write a perturbed initial condition, then the propagation from that perturbed initial condition, and then if you just eliminate y0, then you end up with this expression. So this is what you normally have in a time series, and then you are perturbed by this value, which if alpha is small, is a small perturbation. You can do exactly the same if you also have forcing terms, at which point you have the same perturbed initial condition, but then as you go through, you just accumulate the forcing. So you end up with the expression for each time step. This is exactly what we had before. So this is the circulant all at once operator for the homogeneous part. This is the accumulation of the right-hand side for the standard non-periodic all at once operator. And then this term is the combination of, how this accumulation propagates back into the perturbed initial condition. So if we now look at the convergence rate for constant and exact coefficients, so matching in the preconditioner and the matrix, the right-hand side is very simple because they differ only in a single element. So we can then work out an expression for the error at the next iteration as a expression of the error at the current iteration, and you end up with the standard ParaDiag convergence expression, which is this paper where they showed this for any stable time integrator, so where this magnitude of phi is 1 or less. One thing we can see here, if we stop a step before this, is that we have factors of the magnitude of phi in this expression. For hyperbolic problems where this is 1, it's kind of known, and there's plenty of numerical evidence that we only converge if alpha is less than a half, because if it's not less than a half, this is greater than 1, and everything goes out the window. But for parabolic equations, this is less than 1. So for any reasonable value of n that we might actually be interested in, this essentially goes to 0, and you're left with alpha and the magnitude of phi. So it kind of shows that you get the convergence even up to alpha is 1 for parabolic equations. So the interesting bit now is what we're interested in before for variable and inexact coefficients. So to begin with, we'll just do constant but inexact. So we have phi hat in the preconditioner and phi in the matrix. And again, we just plug in our expressions. My mouse pad is sticking. So we end up with this forcing on the right-hand side, which is just the error between the two propagators. Plug that into our expression for the time series, where we have our initial condition and then a forcing, and we end up with this mess. Start trying to take the modulus of that. Sorry, this is the same expression as we had before. So the perturbed initial condition with the alpha and the error at the last time step. This just looks like a standard integration of the error. So you're just accumulating this in the preconditioner. And then again, we have this term, which is the combination of the accumulation of the forcing in the error with the term coming from the tail term. So if we take the absolute value and reduce everything down, the first two terms with the alpha in, we can use exactly the same estimate as previously. And then for this additional term, we just have a standard approximation of this sum, either from a Toeplitz matrix magnitude or from a finite sum. We end up with this expression, which looks very similar to what we had before, where we have alpha and 1 minus alpha. We have a difference in the propagators, and then we have this term here, which comes from this fraction, which is the minimum of the number of time steps or this value. So if magnitude of phi is 1, this just ends up as, or it approaches n. If phi is less than 1, then eventually it will come to a fixed constant value. So this term will disappear, see it increasing, and then starting to level off. So this section is identical to the MGRIT or two-level MGRIT or parareal convergence estimates. Phi would be phi m or f, fine propagator for your all the way across a single C interval. Phi hat would be your G propagator in parareal, or your phi delta in MGRIT. And if you take out the alpha term, it looks exactly the same as the iteration on the MGRIT show complement or on the course level. But you then just have this little extra increment. So you can tie it back to a lot of existing methods. Show a couple of examples. We'll do advection diffusion equation. Just in 1D, I will vary the diffusion coefficient and the velocity. So it's all simultaneously diagonalizable. You're essentially modifying the eigenvalues. And I'll estimate convergence by the slowest eigenvalue, modest eigenvalue. So if we do constant coefficient, advection on the left, advection on both of them, different theta. So this is trapezium rule, this is backwards Euler. Trapezium rule has no dissipation, and we see in purple and behind it black for the expected rate. If we increase with alpha for various number of time steps in CFL, we are linear in alpha up until we get to a half, and then it shoots up to 1. And the GMRES in green follows very closely. If we add a little bit of diffusion by doing a backwards Euler, interestingly, and I don't 100% know why for this particular case, yes, the purple, the fixed point iterations follow almost exactly the same trend, but GMRES has much faster convergence. That little bit of diffusion, something about GMRES as opposed to the fixed point iterations, you get much better. You wouldn't necessarily want to use backwards Euler with advection, but it's coming from this expression. You can see it even more if you look at constant coefficient diffusion. So if you look at the first iteration, the convergence rate of the first iteration, see it's linear in alpha. This is now our modified convergence rate, so we have these factors in them, and you can see that the convergence rate that we expect in the black line is always less than 1. And the trend is right, it's lower than we'd expected, which is nice. The next few iterations, this is down at 10 to the minus 8. 10 to the minus 8 in 2 iterations, that's machine 0. Essentially what happens is the first iteration with the diffusion equation, it kind of jumps down like you'd expect, and then it just falls off a cliff. It's really non-linear convergence, which isn't described in this. Maybe in the generating function method, there's a way of kind of getting that with the non-linear convergence paper that came out recently. We'll look at in the future. Okay, and the last couple now looking at inexact advection. So this is where constant coefficient advection, but the preconditioner doesn't quite match the operator. So if we look at where we have no diffusion in either, but the preconditioner doesn't quite match, you can see if the U hat is 1, same as the operator, we get the alpha convergence. And then as you increase the U hat away from the U in the operator, your convergence deteriorates, and our expression predicts it pretty well. The dashed line is from this expression, and the trend is right. It's a little bit further up. It's not a tight bound, but it is predicting the behavior. On the other hand, if you have a fixed error in the velocity, so our actual velocity is 1, we have a fixed error in the velocity in the preconditioner, but we vary the diffusion, you can see that our convergence gets worse to begin with, and then we reach a certain point, a certain number of time steps, and it flattens off. Both in the predictions, if we take the green one, the smallest amount, we get to about 4,000 time steps before it flattens off. Our expression is predicting it a little bit earlier, but we do end up tailing off. So fixed point, obviously this won't converge, but it is getting to a capped value. So GMRS does much better, or scales better once you hit this. It's not practical at that point, but it does, you don't keep on deteriorating the convergence. So this is quite low resolution. The thing is that actually just adding more and more diffusion just keeps on getting better and better. You have a diffusion of 0.1 in the preconditioner and it looks great, even though there's no diffusion in the actual operator. If you get to a higher resolution, more reasonable, it flips around and adding a little bit of diffusion does improve things, whereas getting further away doesn't. So don't be tricked by this, that ParaDiag just wants a ton of diffusion. And finally, this is for variable coefficient advection. So in the preconditioner, it is constant at phi hat, but in the operator, it is phi j, and it's just 1 plus some oscillating amount. Again, if we take no diffusion in either, but then we increase the magnitude of this oscillation, if we just assume the worst and we take the max value of this, then we end up with a very similar prediction to previously with those dashed lines. But actually for the same magnitude of the error, the maximum error, versus the constant coefficient case, we actually end up with a better convergence rate. It's a faster convergence and it's not quite as bad an increase, which is possibly why we've still been managing to get speed ups for non-linear problems where you have these oscillations compared to what this would imply, where you end up with like 100 or 1,000 as the magnitude of the fixed point convergence. And again, the point where you have non-zero diffusion, again, it really flattens off. And I don't quite understand yet why this happens so much for the variable coefficient, because this is just a very brute force. I didn't know what to do, so I took the max, and it clearly doesn't describe it well. But for the other cases, it's a reasonable indication. So, we have an open source library for ParaDiag methods. We see really, really good scaling for constant coefficient problems, both algorithmically and in terms of the actual computational performance. We've got modest speedups for non-linear problems. We can see once you start solving multiple windows in parallel, you can start increasing that scaling a bit further. And we've got some new convergence estimates, both for approximate and variable coefficients, which are valid for any stable time integrator. That's putting the convergence estimates of ParaDiag on a more similar footing to the convergence estimates for a lot of other parallel time methods. And then in the future, we want better block scaling, we want better all-at-once scaling. Possibly this will come with combining it with other methods, turning the multi-window into a multi-level, and maybe looking at tighter convergence bounds, either way you get non-linear convergence or where you have variable coefficients. That's everything from me. Happy to take any questions.